understanding the various tests for normality. But before we begin with understanding the test for normality, let's start with the very basics and fundamentals of statistics that we have understood so far. So in statistics, we have understood the very basic concept of a universe and a sample. Now let me begin with a very simple example. I am there for a survey in school. What I can do is I can ask all the 300 students of the school a question, or I can select, let's say, 2 to 5 students from each of the classroom and ask them the question, and based on that prepare my results. Now if I am taking all the 300 students, what I am doing, I am focusing on the universe. But when I am picking 2 to 5 students from each of the classroom and asking questionnaires to them and then proceeding with the results, that is the sample. In statistics, what we usually do is, it's not practically possible to cover the universe, so we move on to the sample. Now understand this point here itself very carefully, that if I am talking about universe, I am having the actual values, but when I am doing a survey on the sample, it is an expected value, and there is a difference between the actual value and the expected value. Clear? So I repeat again, the idea here is there would be an actual value. Let's say if I am doing something on 300 students and finding a detailed analysis, that is the actual value that I have. But I am picking, let's say, 2 to 5 students from each of the classroom, and then I am finding my results, that is the expected value. Now here I am picking the sample. My samples could be biased. So as a statistician, as a scholar, my duty is to keep my samples unbiased. That means I would open-endedly pick students. I would not restrain myself. The students starting with alphabet A, or students starting with alphabet M, or so on and so forth. So that is a unbiased sample that you are collecting, and it is an expected value. Now when you are comparing an actual value and an expected value, what do you think would be the result? So when I have a normal probability curve which I am drawing based on the expected values, and then I am plotting the actual values that are there, or with the actual value and the expected value there is a comparison, the difference between the actual and the theoretical values, we would say, is where you require the test for normality. Clear? So here we would begin understanding the various tests for normality, why they are required and how they are used. Again, when does the normality becomes an issue? If I am having a normal probability curve, as you can see here. So this is my normal probability curve. If the tails have outliers, if there are some values which are outliers, that means all of the students have a similar response, but one of the student is having an extreme response for something. So let's say I am testing IQ or intelligence. All of the students are coming up with a similar response, and one of the student is coming up with either a very poor response or a very good response. That means that is an outlier. That is not something which is within my normal constraints or my normal analysis that is there. So outliers are problematic. If my tails, the normal probability curve, the peripheries, the extremes of the normal probability curve are too much either skewed, if the data is skewed towards one side, if there are too many students with higher IQ or too many students with lower IQ, then there is a variation with the actual and the theoretical findings that are there. Also, there is another problem with a small sample size. If I take my sample very small, out of 300 students that are there in the school, I pick up only 3 students. Those 3 students are not sufficient to represent the whole of the 300 students, and therefore this is a problematic data. So those are the kind of problems that usually a normality test faces. Now, if you perform a normality test, it is very important that you should in neither case ignore the results that are being obtained from a normality test that is there. If my data is not normal, then what would be done? If the data is not normal, then you would go for a non-parametric test. If the data is normal, in that case you would go for the parametric test. Now what are parametric and non-parametric tests? We have covered in a separate lecture. So if you want to go into details of parametric and non-parametric test, you can refer that. And also, if you have the groups of data that are there, you must test each of the group for normality. It's not that you have checked whole of the population at one go. Within the population, if I have created group, let's say it's class 1 group, class 2 group, class 3 group, then I would have to test normality on each of the groups or each of the subsections of the population that is there. So testing normality can be simply done by two important methods. Those are either graphical representation or statistical methods. Of course, as always, graphical method is the most simplest method that we always understand, and then we would go for the statistical method. Usually, if the probability is greater than 0.05, it indicates that the data is normal. However, if the probability is less than 0.05, it indicates that the data is not normal. Again, there are various statistical softwares available in the computing. So, for example, statistical package for social sciences, which is called as SPSS software. So, that software uses the Kolmogorov Smirnov test as one of the tests that is there for testing normality, or it uses the Shapiro-Wilks test. However, if I am going to, let's say, past software would use Jarque-Bera Test. So, there are various softwares and various different statistical methods that could be used. Now, where and when we can use which of these tests is important, and that is something we would understand in a while. So, let's first talk about the two graphical methods. The first is a QQ plot. So, QQ plot is a simple plot where what I do is I plot my values. Now, I have an actual distribution that is there, which is denoted by a straight line, and then I have the theoretical distribution and the actual values that are there. And if those values are very close to the line, that means it's a normally distributed data. However, if there is deviation from the line that is seen, it is a non-normally distributed data. So that is a very simple representation to understand a comparison between the theoretical and the actual data that is there, which is called as QQ plot. The next is the graphical method, which, as we said, is using a cumulative frequency is one of the method. It cannot be applied when the sample size is too small. Let's say I am talking about 3 to 5 samples out of 300, then my sample size is very small and I cannot use a graphical method. Also, a histogram is a method used to explain the graphical analysis, and on the normal curve you would have the actual values that would be plotted and the difference would be seen to detect the normality that is there, whether there is a statistical difference in the data or there is no statistical difference in the data, but that is just merely observed graphically. You are not applying any statistics onto it. So that was the section of graphical methods. Coming on to the statistical method. Now under statistical method, today we would talk about 5 of the statistical methods. Understand this very carefully. The first test that we are trying to understand is WS. Now WS is not the same as Shapiro-Wilks test. Shapiro-Wilks is a separate test. WS test is a test to understand the normality, and a very simple way to explain the WS test is to understand the ratio of the range and the standard deviation. Now here, as you can see in this diagram, I have two different columns that are there. The first column shows the same range. So the W remains the same in the three cases, the range is same, but the standard deviation varies. In the first case, the standard deviation is less. In the second case, the standard deviation is more. The third case, the standard deviation is further more. But the total range, the highest and the lowest values remain the same. So, this is the Q that you would find out, which is also written as U in many of the literature. So Q or U, which it is written with the result of WS test, would give you a ratio between the range to standard deviation. So in the first case, we have the range that is constant. In the second case, my range is changing. The first case, the range is less. The second case, the range increases. The third case, the range further increases, but my standard deviation remains the same. So, those are the two cases that we understand, and WS is one of the very simple, standard, easiest way of understanding the test of normality. The next important test is Jarque-Bera test, which is used in the past. Now past, when talks about the Jarque-Bera test, it is mainly used for large sample size. When my sample size is big enough. If I have smaller samples, this is not a successful way of using it. Now in this formula, N stands for the sample size, S stands for skewness, and K stands for kurtosis, and based on that you have the results for Jarque-Bera test. Jarque-Bera test, if the sample size of 2000 or greater is seen, that means it is comparable to a chi-square distribution of 2 degrees of freedom. Okay, degrees of freedom we have covered separately, so refer that if you have doubts about understanding the concept of degree of freedom. Now, this is where we have the chi-square test with 2 degrees of freedom. It is equivalent to that, and it is, as we said, used for the cases where the sample size is large. So I repeat again, Jarque-Bera is a test which is used when the sample size is big enough, and it is used to understand the normality as in whether you would go for a T test or F test could be run to understand once you have the normality values that are there. The next is the Shapiro-Wilks test. Now Shapiro-Wilks, as we said, is the test which is used through the SPSS software. Now here, what we are trying to do is, the ratio of the numerator to denominator here is the observed by the expected. Now in all of these methods, the logic remains the same. The observed to the expected values is what we are trying to understand. The test here is biased by a small size sample. So a small size sample is not considered a good idea to understand a Shapiro-Wilks test, and also continuous data is a prerequisite. So it is applied to a continuous data, not a discrete data. A discrete data is a data which is true false. A continuous data is, let's say, the height of a child or a weight of a child which is constantly growing. When I say 3 feet and 4 feet, it is not just 3 feet and it directly jumps to 4 feet. It is 3 feet, 3.1, 3.2, and it's a continuous data till 4 feet. However, when I say, if your question is, mark the question as true or false, it can either be true, it can either be false. There is no middle divisions that could be seen. Okay, so Shapiro-Wilks test is applied for a univariate continuous data that is there. It is biased if the sample size is small enough, and if the null hypothesis is true, usually the value of W should be 1, and that is one of the important ideas that we need to understand. And here the values of xi explains ordered random values that are there. So that is the Shapiro-Wilks test in a very simple understanding as a test of normality. The next is Kolmogorov Smirnov test, which is also known as the KS test. This is another important test which is used through the SPSS software, commonly applied, but you need to understand the logic again. Again, in this case, we have the observed to the expected values of the cumulative relative frequencies that are there. So, observed cumulative relative frequencies to the expected cumulative relative frequencies are calculated with the help of Kolmogorov Smirnov test, and this is based on the EDF function, which is empirical distribution function, and it is very important to note that it again applies to a continuous distribution. It tends to be more sensitive near to the center of a normal distribution rather than the peripheries or the tail of the normal distribution. So the values are more sensitive towards the center of the data rather than the peripheries that are there. Again, as I said, it is applied to a continuous distribution, and in case the calculated values are less than the critical values, that means there is an acceptance criteria for the null hypothesis. And when there is an acceptance criteria for the null hypothesis, we go by the same rule again of understanding and accepting the normality. The next is de-agnosto test. Agnostino test basically talks about how much we are away from normality. So departure, so D here stands for departure. That is something that you can understand here. So it's basically understanding departure from normality, and it's a very effective test to understand how away you are from normality. Now D is the test static. You have SS as the sum of the square data that is there, and T is the value that you would be finding here. Also, the whole concept is very important to understand in case of D'Agostino test is that if the sample size increases, if there is bigger sample size, the probability decreases. So, when we are talking about normality and understanding of normality, there are few basic highlights we need to know about each of the tests. First of all, a quick recap of these tests again. So WS test, graphical was very easy. QQ and the graphical method with cumulative frequency, which we understood, which is merely a visual understanding between the difference of the actual and the theoretical distribution. Now here, WS test is a very good test if the distribution is symmetrical and there are smaller tails that are there. If the tails are not longer, there are smaller short tails, and it is cutely presented symmetrical distribution, then WS test is good, because you have to simply find, as we said, range and standard deviation, one of the easiest tests to go. But if the values, if the path is skewed, if it is asymmetrical, it is not applicable. So WS test cannot be applied in that scenario. The next is Shapiro-Wilks test. Shapiro-Wilks test is applied again with symmetrical short data, but it is also applicable if the long tail data is there. So it's applicable with short and long tail data both. WS test applicable only with short-tailed data. D'Agostino is the departure from normality. So it is again powerful when the data is symmetrical in nature and the distribution is long-tail. In case of short-tail distribution, D'Agostino test would not work well. Okay. Then is Jarque-Bera test. Jarque-Bera test is again good, and it is very similar to D'Agostino. That means it is good with a long-tailed data. Okay. If the data is long-tailed, then Jarque-Bera test would work fine. And finally, you have Kolmogorov Smirnov, which is one of the most commonly performed data test for normality, and it is important because it is applicable to both discrete as well as grouped data. So it's not just applicable to either, but it is applicable to both either the discrete data or the grouped data that is there. So it is again called as a distance test, since it is applicable to both of those, and it is also known as the goodness of the fit test. So one of the very important tests among all of the statistical tests. A quick understanding of why we apply these tests of normalities is very important. I come up with the same concept that we understood in the beginning, that we have a universe and a sample. When we are not able to capture whole of the universe, what we have to go by is the sample. We have to select the sample very carefully. It should not be too small, too skewed, or it should not be biased. And from the sample we have the actual values that are there. We compare those actual values to the theoretical values, and the difference between those is represented through the test of normality. So this is the basic concept and a basic understanding. Once you have that, and if you are familiar with any of the statistical softwares, you can quickly apply any of those tests and get a result. But the concept, the logic is very important. Why actually we need to have a test of normality? We would be covering many interesting lectures on the test of normalities and statistics in the upcoming sections. So stay tuned for many lectures from our side on higher order statistics. Have a wonderful day ahead.